Greetings from Calgary. Today I'm going to be doing the second of my Gadgeteer motor series, focusing on using servos with Gadgeteer. After looking at my last presentation, I thought I better do some of this in a PowerPoint presentation so I can clearly show how Gadgeteer and servos work together with pulse width modulation. A servo motor is a rotary actuator that allows for precise control of angular position, velocity, and acceleration. It consists of a suitable motor coupled to a sensor/encoder for position feedback. A servo motor consumes power as it rotates to the commanded position, but then the servo motor rests, which is different from, say, a stepper motor, which run warm to the touch because they continue to consume power to lock in and hold the commanded position. Servo motors are controlled via pulse width modulation. And as the pulse width changes, so does the angle the motor rotates to. The amount of power applied to the motor is proportional to the distance that it needs to travel. So if the shaft needs to turn a large distance, the motor will run at full speed. If it needs to turn only a small amount, the motor will run at a slower speed. This is called proportional control. These motors, by design, usually only turn some portion of a circle. For example, I have two HiTec HS-422 Servos that I'm using, and they turn from -90 to 90 degrees, or half a circle of rotation. To do this, the HS-422 motor interprets a pulse width from 600 microseconds to 2400 microseconds to an angular position from -90 to 90 degrees. So basically the angular position of the motor is set by the pulse width. Note that unlike using pulse width modulation with DC motors, with servos the pulse width modulation is a command signal, whereas with DC motors you use pulse width modulation to deliver a controlled amount of power to the motors. So my objective for this Gadgeteer project were twofold. First, build a project that would let me experiment and learn about controlling servos. And I wanted to control both traditional servos and continuous rotation servos. The second objective for this was to create a servo driver that would simplify servo development for other Gadgeteer developers. So given servos use pulse width modulation, it would make sense that a Gadgeteer module would use a P socket, which is a Gadgeteer socket focused on pulse width modulation. Gadgeteer uses a 10-pin socket, and so using the Gadgeteer standard for a P socket, we can have a pulse width modulation output on pins 7, 8, and 9, and for the moment just note that we can have a general purpose I/O on pins 3 and 6. So this means that we can control 3 servos with a single P socket. Now we can use an extender module, or a breadboard and wire this up, or we can use an existing Gadgeteer servo motor expansion module from DFRobot, or a tiny servo module from Ingenuity Micro. I'm going to use the DFRobot module, which costs $6.50. This module expands the Gadgeteer socket to 7 digital outputs. Through the onboard switch, you can select whether using external power or internal. So I'll set it to use the internal 5 volts, which should be okay for this experiment. If I was going to use these servos under load, I would likely switch to using an external power source, as servos can be power slurpers under torque, so you might not want them using the same power as your control system. Now I'll do another video on how to make a module driver using this code, but for now I just wanted to show the lower level code for driving a servo, showing how we create a pulse width module output on a pin, and for this module I wanted to add some interrupts so I could add some Opto Interrupters, i.e. beam breakers, to take advantage of the 2 general purpose I/O pins. All I have to do is plug the module into a suitable P socket on the main board. So in this case I'm using a FES Hydro board, so I'm going to plug my module into socket 7, which is a P socket. As a software developer, all I want to do is say which socket I plug the servo expansion module into. And once I've converted this into a proper module driver, the designer will take care of that for me. I might have to configure the servos as per their specification sheets, because not all servos are the same, and I highly advise you review your spec sheet before using a servo. But this is all I want to do, and this is the beauty of Gadgeteer, as it makes hardware this easy to use. .NET Micro Framework even makes the low-level stuff easy to do. GTI is the Gadgeteer.socket interface library. The socket is the socket we plug the module into. The pin is the Gadgeteer socket pin that the signal is being sent to, and false means we're not inverting anything. And of course there is a reference to the module itself. I decided that I wanted to control the servos in terms of angle or percent, so everything pretty much translates these to a corresponding proportional pulse width module pulse width as given by the min and max pulse width for the servo. So given I'm using a HiTec HS-422 and even the HS-425 continuous rotation servo, the min pulse width is 600 microseconds and the max is 2400 microseconds for -90 and 90 degrees respectively. So for example, if I wanted 0 degrees, known as centered, or 50% rotation, I would need to send the servo a pulse width of 1500 microseconds. Now there were some additional features that I would like to add to my library. I would like to be able to give it a command to center it, or go to the min or max positions, or I'd like to be able to ask it what the current angle is. So basically have it store its angle or percentage or position. And in some cases, some people have asked that I be able to reverse this. So I guess if the servo is inverted or whatever, they'd like to be able to just say is reversed. Now for the continuous rotation servo, I want to be able to set the speed, stop it, or ask it what the current speed is. So at the module level, a lot of our code is to convert some target value to a pulse width. So for example, if we give it an angle, we've got this, we're looking at the ratio of what the angle is to the range, and then we convert it out that way to what a pulse width ought to be, and then we tell the servo to set the pulse width cycle, which is 20,000 milliseconds, and that's the frequency of the pulses, and we give it the pulse width, and then there's a factor that says that we're using microseconds, and then that rotates the server to that position. Now lately I've been salvaging a lot of old printers, as they're a good source for motors for experimenting with, as you often get 3 or 4 motors from a single printer. You can get stepper motors, DC motors, some with built-in encoders or at least external encoders, or brushless motors, etc. But one of the things that you'll find when you take apart a printer is usually lots of opto interrupters or beam breakers. And so I wanted to make my continuous rotation servos reverse direction when one of these beams is broken. Think of it as like a motion limit control. When a limit is hit, the device reverses its direction. So we have to create the interrupt for that, and it's so at the module level, we're dealing with the pins and such, but at the other level, we don't have to worry about it. It's just going to be an interrupt that gets raised into our application. So for my test example, I have hooked up potentiometer modules to control the 2 HS-422 servos. One potentiometer is used for setting the percentage of rotation, while the other is used to set the angle of rotation. In the servo objects, I store the position requested, so in the case of the button clicks, I can move the position of the servo incrementally by some percentage or angle. So in the spirit of Gadgeteer, I've really simplified how to use servos, as all the hardware level code is in the module drivers. Now the HS-422 servo is a continuous rotation servo, which is the same as the other servos except the mechanical stops have been removed and the servo always believes it's at 0 degrees. So if I set the servo to say 20%, the servo will move like it's going to 20%, but it'll never get there, so it just keeps rotating. So in a sense, it's like a regular DC motor where you have a simple speed control built in. Certainly it's an option, for example, as a drive system for a rover. So controlling servos with Gadgeteer is really easy to do, and it's even easier to do if you use my servo control module, as then you can treat the servos as an object with methods to control it in easy terms without having to know about pulse width modulation or pins. Gadgeteer is happy to let you play at whatever hardware level you want, but for software developers, Gadgeteer's hardware abstraction just makes perfect sense. Now before we actually play with the device, let's just have a really quick look at the code just so we kind of know what's going on when we're watching things. So you'll note here that this is where we're just adding this module manually. When we do this as an actual module driver, this will be handled for us in the designer. So you'll actually see this board appear and connect it in there, and then that's all we have to do with it. So for now we have to manually connect it. And then so when we reference servers, I had talked to some people and they were like, well, why don't you try it as an array of servers? And so that's what we've got. We've got servos 0, 1, and 2. So these top two guys here, these are the normal servers, the HS-422s. And then the one down at the bottom is HSR-1425 CR, so it's the continuous rotation. And then we have the interrupt sensors. These are the beam breakers that I put on, and then we just got some buttons for some control. So we'll just take a look at this. So one of the buttons, we are actually doing a turn percent 5%. So that's an incremental 5% turn. As I mentioned, we store the position of the servo within the servo object. Same with turn angle. And then while we're here, we'll look at the interrupt sensors. So when these go high, when the value is true, what we're going to do is we're going to grab the current speed of the continuous rotation servo, and then we're just going to reverse it, so it's going to go back. And same with the second sensor, the same sort of thing. It's just going to reverse the direction. So in our timer event, we have turn to angle, which instructs the server to turn to a particular angle. In this case, it's between -90 and 90. And then we have a turn to percent of rotation. And then at the bottom here, this is the continuous rotation server. We just have a set speed. And that's all the code there is. Now, as always, I'll post the source. I'll post the source code links below so that you can have a look at this, and we'll include the source code for the driver for this card and stuff like that. Like I said, in a future video, we'll do. I'll show you how to take this and convert this into an actual module driver. It's actually it's easy once you've done it once, then you'll sort of go, oh man, I'll do this with everything. But let's fire this bad boy up and see what it looks like. So we'll start the debugger, and then we'll switch over and have a look at the actual device itself. So on the device, you can see that actually here is the DFRobot module, and it has my my modules all plugged into it. So these two wires here are actually going up to these beam breakers, Opto Interrupters. I love that name, but they're just beam breakers. And then we have our potentiometer modules down here, and then to control the continuous rotation, I'm using this slide control. So if we come in, and we can see that our first servo, we're dealing with percent rotation. The second servo over here, so this is percent rotation, this is angular rotation. Like I said, this is a continuous rotation. I stuck a wire on it so it's easy to kind of see it turn. So if we take this potentiometer, we can control the server as much as we want with that, and then same with the second one. We can control it as much as we want. Now if I hit this button, it's going to move it 5%. You can see that we're moving small increments, so servos are very accurate in terms of incremental turns, and that's how those work. So now if we just kind of turn that, they should center themselves back up. Now we'll go over here and we'll take a run at running the continuous rotation server here. So if we turn it up just a little bit, we have some speed control on it, and then if we go full speed or full reverse, and again we can kind of slow that right down. It doesn't have great speed control on it, but it does have some. So now I'll just grab something here, and we'll put her up full speed, and then I'm just going to take something and slip it in here so it breaks the beam between, and you should see it reverse. Right, and that's all these opto interrupters do. They're an optical switch, and we just use them to reverse the direction. And so there, turn the override off, and there we go. We'll just turn that off. So like I said, as always, I'll post the source code below. And again, Gadgeteer is a great platform for people wanting to build devices, but maybe don't want to spend a lot of time learning how the hardware works and such, because when you use Gadgeteer modules, you're just dealing basically with the routines that you want to do, and the pin level and such stuff is in the module drivers. Now if you want to get out and breadboard stuff and you want to play at the pin level and everything, Gadgeteer is happy to let you do that. So until next time, happy Gadgeteering.